And we're rolling.
We are rolling. 7.3, page 197.
Bless you.
So the gas giants are all pretty much the same in composition. Low density, made of hydrogen and mostly hydrogen and helium. 98% of these gas giants are hydrogen and helium.
Will they ever become solid?
Well, not on the surfaces, but in the very center of them, like it said in the video yesterday, the pressures get so high that it pushes the material together into a solid. So they do have a solid core. And outside of their solid core, there is a liquid metal hydrogen portion, where the hydrogen atoms have been pushed close enough together to make them liquid, and they take on the electron structure of a metal so that they conduct electricity real well. So there's liquid metallic hydrogen surrounding a solid core. The solid core has some rocky materials, and the solid core is about 4 times as wide as the Earth is. So they do have a pretty big solid core. But the planet's so heavy that the hydrogen and helium atoms stay with the planet. They don't float off into space. If you release helium here on Earth, it's light, it'll go, and it'll be lost into outer space. Earth doesn't have enough gravity to keep in helium or hydrogen. Hydrogen is light too. So, but that doesn't escape a gas giant. And these gas giants, remember, were orbiting. We're going around way further from the sun than the Earth is. And so the gas giants collected a very large amount of stuff in their orbits as they were forming. And so the gas giants contain a lot more things. The Earth and Mercury and Venus a lot further in had, short orbits, so there wasn't as much stuff to conglomerate into our planet as there was that conglomerated into these big gas giants. So that's why the planets that are further from the sun tend to be bigger. And this is a nice little table showing you the sizes, masses, and such. You can see Jupiter 320 times the mass of the Earth, with Earth equal to 1. Jupiter is heavier than all the other planets combined, by a lot, a big margin. Jupiter is also bigger in radius. 11 times the radius of the Earth. So it's a lot heavier and a lot wider. You can see the density here. Look at Saturn. Saturn has an interesting density, 710 kilograms per cubic meter. Do y'all know what the density of water is? 1,000 kilograms per cubic meter. So Saturn is lighter than water. If you took Saturn and you could put it in a bathtub, imagine a giant bathtub, it's kind of a silly thing to imagine, full of water, Saturn would float. Saturn's density is less than water. All the other planets are more than water, but you can see the gas giants are significantly less dense dense than the terrestrial planets. And guess which planet is the most dense? Earth. We have the densest planet. Yay. Yay for us. If you could stand on the surface of Jupiter, you'd weigh 2.5 times what you weigh on Earth. So I'm about 150 pounds. I'd be about 375 on Jupiter.
Get a good workout.
If it had a surface. It doesn't, though. Fall right through the surface. But if somehow you could have a floating platform that you could stand on, you'd be heavy. Yeah, that'd be a good workout. I wouldn't be able to stand. Well, I would, because I'm real strong. But you guys wouldn't. That was a joke. Just feel free to laugh if you ever hear anything funny. You can see the escape speed is 60 kilometers per second. You aren't getting away from Jupiter's gravity very easily. Here it's 11 kilometers per second. Interesting thing about the gas giants, they rotate very fast, even though they're real big. Look at the rotation rate for Jupiter. 0.41 days. So Jupiter actually spins around faster than Earth does. Way faster. And that has to do with the fact that it's a gas and it can move quickly. The winds in Jupiter's atmospheres are real high. Approaching 600, 700, 800 miles an hour. Or even faster. It has what's called a differential rotation. So it rotates faster in the center than it does at the poles. And Jupiter doesn't have much of a tilt to it. A 3-degree tilt. That means Jupiter is almost straight up and down. Saturn has a 27-degree tilt. That's about what Earth is. So Saturn's tilted like Earth. Saturn has seasons. Look at Uranus. Uranus has a 98-degree tilt. That means Uranus is laying on its side. Nobody knows why that is. It probably had an impact early in its formation that knocked it on its side.
Do you still have seasons?
You would have seasons if you're on your side. Because if there's the sun over there, when you get on the other side of the sun, now the sun's at this, looking at this pole. And then when you get on this side of the sun, now the sun's on this pole. So you would have seasons.
How do you tell if it's laying on its side? It's just a circle.
Well, because of its, that's a good question. Because of its rotation. So this is straight up and down. This is on its sides. Good thinking, Olivia. That's not evident right away.
Silly goose.
What about the surface temperature? It's cold on the gas giants. Brr. 58 Kelvin. Kelvin is 0 Kelvin is absolute zero. Nothing gets absolute zero. That's kind of a theoretical number, but that's the absence of any molecular movement. And these are 58 Kelvin. That's pretty. I mean, on Earth it's 290 Kelvin is average. That's about 70 degrees or so. Maybe 65 or something like that. I'm not sure what the average Earth temperature is. That's a good trivia question. And look at the magnetic fields. If Earth had a magnetic field of 1, Jupiter has a magnetic field of 14. Very high magnetic field for Jupiter. And it extends way out into space.
Wait, are Jupiter, Saturn, Uranus, and Neptune like all the same, made of the same gases?
They are.
So how come they're different colors?
Well, that has to do, we're going to talk about that. That has to do with the different temperatures. And there are some things. There's some methane and some other things that help give it color, but if it's hotter on the surface, you'll see the colors better than if it's cooler on the surface. But there are some variations in some of the things. We're going to talk about that. That's is it today? Yeah, we start talking about that in just a few minutes. It's a good question. There's the Earth in comparison of size to the other planets. It might look like in this picture that Saturn and Jupiter are the same size, but that's not true. Jupiter's bigger than Saturn. The rings help make it look like Saturn's bigger. Oh, there you go. There's Saturn floating in a bathtub.
What's that thing at the end? Is that like the drain or
It's
something?
the drain, I guess. The gas giants have differential rotation. Different parts of their atmospheres move in different directions at different speeds. So the equator moves at a different rate than the poles do. The equator moves faster than the poles. It's not that big of a difference. On Jupiter, it's 6 minutes. The equator moves. The equator moves around in 9 hours and 50 minutes, and the pole moves around 9 hours and 56 minutes. But it is different. And you can only get that if your planet's made of gas. A solid structure can't differentially rotate. But Saturn, the difference is greater, 26 minutes slower at the poles. And on Uranus and Neptune, the poles go faster than the equator. 2 hours faster on Uranus and 6 hours faster on Neptune. That's kind of strange. We talked about the variable tilts already. Jupiter is almost straight up and down. Saturn and Neptune are tilting about like Earth is. And Uranus is all the way on its side. Already talked about those.
Wait, don't go yet.
Yeah, I already talked about
I
those.
just finished the first.
I talked about those when you were gone. Okay.
Okay.
Here we see Uranus tipped over on its poles. Tipped over on its side, I mean. And there you go. In 1986, Uranus's, I guess, North Pole was pointed to the Sun. And in 2028, Uranus's South Pole will be pointed to the Sun. So where is Uranus right now? It's about right here in its orbit. 2007. You see, Uranus takes a long time to go around. It takes how many years? Are y'all quick in math? No? 86 years. 84 years. 84 years to go all the way around once for Uranus.
Well, it's 84 Earth years.
84 Earth years, 1 Uranus year. Good job, Michael. Okay, let's look at Jupiter. Jupiter's atmosphere. Jupiter has what's called zones and belts, regions of high and low pressure on Jupiter's surface layers. And that's due to a process called convection. Do y'all remember what convection is? Give me an example of convection.
A lava lamp.
A lava lamp, very good. When something gets hot, it rises, and then it'll cool off if it gets away from the heat source, and then fall back down. Great example. And that's happening on Jupiter. The gas inside the planet is really hot, because wherever you get a lot of pressure, because of gravity, it makes things hot. And then that heat will cause convection, the gases will rise, they'll come up to the top, and then they'll fall back down. So we have convection going on inside Jupiter. And that leads to different colors on the surface. Colors are different due to different temperatures and pressures affecting cloud chemistry. So let's look at Jupiter. Jupiter's got stripes, you see. And zones, the zones are where the material rises and is coming up, and it kind of goes out on either side. And so when it rises, it kind of spreads out and becomes a little bit thinner, and that's a lighter colored zone. And then it'll fall back down, and where it's falling back down, it kind of gets a little bit denser and gets a little darker. So dark is called a belt, and light is called a zone. Zone, belt. Zone, belt. Zones are light. That's where stuff is rising. Dark is a belt. That's where stuff is falling.
What do you mean by stuff?
Stuff is gas. Hydrogen gas, helium gas, and some methane gas. And some water gas. There's actually water in these clouds. Interesting, the zones move in one direction and the belts move in the opposite direction. So if you look at these arrows right here, the zones, the gases of the zones are going this way, and the gases of the belts are going that way. So these light-colored zones are moving from right to left on the picture. And the dark-colored belts are moving from left to right. So if you were floating around on a balloon on Jupiter, which you could if you had the right type of balloon, then you'd be going that way. You'd be going that way if you're here, and then if you get over here, you'd start going in the other direction. One day we might have balloons floating around on Jupiter. The sci-fi writers think about cities where we make this big balloon that has a platform and a covering, and we have oxygen in there, and we float around on the surface of gas giants. And the reason why they think you could do this is because there's a layer of water in these clouds. And you could use the water, you see, for a lot of things. For drinking, for growing plants, for making fuel, because water can be separated into hydrogen and oxygen. And hydrogen and oxygen are fuels. And so why not have a big city in a bubble floating around on Jupiter's atmosphere? Why not? If you find the right sci-fi book, you can read about the wars between the cities, and they float by each other, and one's on a zone going this way, and another's on a belt going that way. And they pass each other every once in a while and maybe exchange some goods. Does that sound exciting? These zones and belts are huge. You could fit a whole Earth in one zone. I mean, that's how big they are. They're bigger than the planet Earth in width. Jupiter has a layered upper atmosphere, which was measured when Galileo sent a probe through the atmosphere. So the upper part of the atmosphere has layers to it, and we know what those layers are because of that probe that was shot out of the Galileo satellite that was going around Jupiter. It shot a probe into Jupiter that I showed you the video yesterday, and the probe went down and took measurements, and so now we know what this atmosphere is made of, down to about 150 miles deep into the planet. And then the pressure was so high it crushed the probe. But here's what it's made of. This line right here shows the temperatures. It took temperatures down to about that deep before it was lost. And it's got a real wispy atmosphere up high. I mean, the atmosphere is thin starting out, and then it gets thicker and thicker. And there's a layer of ammonia. There's a layer of this stuff called ammonium hydrosulfide that would smell like sulfur, like rotten eggs. And then there's, look at that layer of water. Water and ice. And so here's one atmosphere of pressure. If you floated your big city on your balloon about right here, that would be a normal, we'd be at normal pressures. We wouldn't have to pressurize the cabin, the city very much. And maybe little tubes could reach down and grab the water ice that's a little bit lower. It layers like this because these molecules are different weights. Water is heavier than ammonium hydrosulfide, and ammonia is lighter. So the ammonia floats a little bit higher than the water ice does. If you poured ammonia and ammonium hydrosulfide and water into a glass, it would layer itself just like this. All of those kind of floating on top of the hydrogen, helium, methane, and water gases below, which are actually at higher pressure. The pressure makes the gas even heavier, the higher pressure than these things, than these ices. Interesting and weird. That is the area where the probe went into the clouds. Of course, that's changed since then because it all moves and changes. But if you were wondering, that's where our probe went in. Have you ever heard of the Great Red Spot?
Yes.
That's a big storm. So are white ovals, so are brown ovals. Big storms sustained by zonal flow on either side of the spot. Again, the Great Red Spot storm has been around for at least 300 or 400 years. As long as we've had telescopes, it's been there.
Just like a huge storm, like
it's a huge hurricane.
But that's just there all the time?
Yep. It's a hurricane that won't stop. The white ovals, brown ovals, also large storms, but they don't last as long. White ovals and brown ovals might come about and then kind of die out and spread out, and they may only last 30, 40 years. Brown ovals might last 100 years. Or they might only last a few weeks. But what happens is you have two zones moving like this, where the gases are moving opposite one another, and that spins around a little storm, you know? If you got something moving this way and something moving this way, that'll spin anything that's caught in the middle. And so here is the Great Red Spot, and these gases are going this way, and these gases are going this way, and that spins around the Great Red Spot. And here's the Great Red Spot and compared to the size of the Earth. So the great red spot is about the size of the Earth. You could fit the Earth right there inside the great red spot. And you can see one of the zones is also about the size of the Earth. Here's one of the zones here. And there's the Earth. Our video that I'm about to show you more of, I got the atmosphere video back. It shows you the movement in time lapse. Here's some little tinier storms. Here's some storms, and you can see the storms kind of moving past. There it is, and here it is here, and here it's moved past the red spot. And here's a smaller storm kind of getting spun past the spot, and the red spot kind of messed up that storm. As that storm went past, it kind of died out. The red spot kind of knocked it out. So these storms interact with one another. And we'll talk about Saturn next time. I want to continue the atmosphere video. I've already got the test made out, and questions from this video are on it. So I want to make sure you see this. We already saw the Kittinger falling.
Do you want me to stop recording, or
What'd you say? Somebody say something?
do you want me to stop recording?
Yeah, you can stop recording. Do y'all remember